Guys, in this video I'm going to show you guys how to convert your mass of your product into moles of product, and then use percent yields and stuff like that. Okay, so first of all, we did a precipitation reaction. So we had calcium chloride in the aqueous state reacting with sodium carbonate, also in the aqueous state, to produce calcium carbonate. And that is our precipitate. And sodium chloride, which is soluble in water, so it would be aqueous. Calcium carbonate is the same thing as chalk. Next, or very soon, we will start talking about solubility rules. So we'll see why calcium carbonate is insoluble. But because it is insoluble in water, it is going to be our precipitate. So when you added your two solutions together, the white stuff that formed was your calcium carbonate. Thinking about this equation, we can look at this. This one's what's called our molecular equation. But anything that's a strong electrolyte, which we have already talked about, that is in the aqueous state will be broken down into ions in what's called our complete ionic equation. So this would be Ca, and the charge on calcium is +2. Then we have 2Cl minus because of this 2 right here. And then we have, because of that 2 right there, 2 sodiums. So 2Na plus aqueous and CO3 minus 2 aqueous goes to our solid, CaCO3. It is a solid, so it's not dissolved, meaning it's not broken down into ions like strong electrolytes will do. And then we'll have 2Na plus aqueous and 2Cl minus aqueous. So our complete ionic includes any ion broken, or any strong electrolyte or ionic compound broken down into ions. Anything that shows up same state, both sides, would be a spectator ion. So that'd be sodium and chlorine. They are not doing anything. They are spectating. They are floating around. They're not reacting, so they can be removed in our net ionic, which would just be our Ca plus 2 aqueous plus CO3 minus 2 aqueous going to CaCO3 solid. Okay, so this is what we're doing in our problem, and we're trying to figure out how much of this product we're forming. So during lab, you should have gotten 2 numbers. You should have gotten your mass. Well, sorry. I guess you probably got 3 numbers, but you got your mass of your initial compound. You got your mass of your filter paper and your mass of your dried product with the filter paper. So we had 1.470 grams of our calcium chloride, which was dissolved in water, and then it was reacted with the sodium carbonate. Sorry, sodium carbonate, which we had 0.0200 molar, I believe. And we had 100 milliliters of it. Unless I am making this up, which is entirely possible. I'm gonna just make sure that I'm not making this up. Lab 6. Oh, but it's 0.2 molar, not 0.02. Okay, so those are the 2 things that we are adding together. And then we also had our massive filter paper. In this example, I'm going to use 0.175 grams. And then we have our massive filter paper plus dried product, which in this example, I'm going to use 1.032 grams. Okay. So we're going to use these pieces of information to figure out how much product we actually isolated, the grams in grams, how many moles that is, and then that will be what's called our actual yield. So that is what you actually isolated and weighed. Then we're going to go back and look at what we started with and how much we should have made, which would be our theoretical yield. So let's start out with our actual yield. So our actual yield, we have 1.032 grams of our mass of our filter paper and our dried product. We subtract out our mass of our filter paper. And what we're left with is just product, which we should know is our CaCO3. So taking our 1.032 minus 0.175, we get 0.857 grams of CaCO3. CaCO3, if we want to go from grams of CaCO3 to moles of CaCO3, we need to divide by the molar mass. So calcium carbonate, calcium has a mass of 40.078. Carbon has a mass of 12.011, and oxygen has a mass of 15.999. When we add those together, multiplying by 3 for our oxygen, we get a mass of 100.089 grams per mole. So we're going to take our mass of our product, divide it by our molar mass. We see we're canceling out our grams of CaCO3, leaving us with moles of CaCO3. And this gives us 0.00856 moles of CaCO3. So this is our actual yield in grams. And then this is our actual yield in moles. Okay, so now that we have those two numbers, we are going to move on to what we should have gotten based on the numbers we started out with. Okay. So again, we need to think about our balanced equation. So CaCl2, I'm going to leave out states this time. Na2CO3 going to CaCO3 plus 2NaCl. So from this equation, this is a balanced chemical equation. And we can kind of think about this as all of them being in moles. So 1 mole of calcium chloride reacts with 1 mole of sodium carbonate to produce 1 mole of calcium carbonate and 2 moles of sodium chloride. We haven't gotten to stoichiometry yet, but essentially, stoichiometry is just another way of doing dimensional analysis. So we can set any one of these two things equal to each other. So we could say that 1 mole of calcium chloride is equal to 1 mole of calcium carbonate. We can do the same thing with our sodium carbonate and calcium carbonate. So 1 mole of sodium carbonate is equal to 1 mole of calcium carbonate. So these are all 1-to-1 mole ratios, with the exception of the sodium chloride. Sodium chloride, everything's a spectator in there, so we don't really care about it. But that's essentially what we're doing with stoichiometry, is we're just looking at our balanced equation and making conversion factors. So we are starting out with 1.470 grams of CaCl2. And using this idea, we can figure out how many moles of CaCO3 we should have formed. So first we need to get our CaCl2 into molar mass. So calcium again is 40.078 grams per mole. Chlorine is 35.453 grams per mole. So we get a molar mass of CaCl3. Oh, 1 second. Of 110.984. So we're going to convert this into moles by dividing by our molar mass, 110.984 grams. Which gives us 0.01325 moles of CaCl2. And we know, again, 1 mole per 1 mole. So 1 mole of CaCl2 is 1 mole of CaCO3. And then this would be our theoretical yield, how much we can theoretically make. Well, actually, we don't know if that's true yet. Sorry, scratch what I said. Okay, and then we'll come back to that in just a minute. Remember, our mass of calcium carbonate is 100.089 grams for every 1 mole of CaCO3. Which gives us 1.326 grams of CaCO3. We need to do the same thing using our sodium carbonate. We're trying to figure out which one would make the least amount of product. Whichever one makes the least amount of product is essentially the one that gets used up first. And then that gives us what our theoretical yield, the maximum amount we could potentially make for this reaction. So we had 0.200 molar Na2CO3 and 100 milliliters of that. So if we have molarity and volume, we can multiply them together to get to moles. So we have 0.1000 liters. So I've just taken that 100 milliliters and converted it into liters of our sodium carbonate solution. Multiply that by the molarity, 0.2 moles of Na2CO3 for every 1 liter. And then we already know that 1 mole of Na2CO3 produces 1 mole of CaCO3. So multiplying that out, 0.1 times by 0.2 times by 1/1 gives us 0.0200 moles of CaCO3. One second. I put the wrong number in. I am so sorry. This is supposed to be CaCl2.2H2O. Sorry about that, guys. I forgot about that. So we have 1.47 1.470 grams of CaCl2.2H2O because this is a dihydrate. And then 1 mole CaCl2.2H2O has a mass of 147.0 grams. Which gives us 0.0100 moles of CaCl2.2H2O, and that's a dot 2H2O, which gives us 0.0100. We have one more zero. 0 moles of CaCO3. My apologies. Which would then give us 1.001 grams of CaCO3. Okay. Very sorry for those issues. Okay, and then we take our 0.0200 moles of our calcium carbonate. So going back to this part, multiplying by the molar mass of calcium carbonate. Giving us 2.00 grams of CaCO3. As a note here, this actually would probably be 1.00 grams. Now, comparing this versus this, we can see that our calcium chloride dihydrate produces a smaller amount of calcium carbonate, telling us that this right here is our limiting reagent or limiting reactant. So this limits the amount of product that can be produced. Once we run out, we can't make any more. So this would be our theoretical yield in grams. And then this would be our theoretical yield in moles. So our sodium carbonate is in excess. So this would be our excess reactant. So we don't need to use the calculations from our sodium carbonate because we're not going to be able to produce that amount of calcium carbonate, as we will run out of calcium before we can get to that point. So we're going to use 1 gram as our theoretical yield in our calculations. So we have 1.00 grams of CaCO3 as our theoretical yield. So this is the maximum that can be made based on our limiting reagent, our calcium chloride dihydrate. We solved earlier for our actual yield. So as a note, our actual yield was 0.857 grams. So this is what we did make. This was the maximum amount we could have made. So the last thing we need to solve for is our percent yield. So taking our actual yield, what we weighed out, divided by our theoretical yield, what maximum amount we could have made, and multiplied by 100%. So this would be 0.857 grams of CaCO3 divided by 1.00 grams of CaCO3 multiplied by 100%. The grams of CaCO3 cancel out and we get 85.7% yield. We also have a percent error, which is essentially going to be the difference between the theoretical yield and the actual yield divided by our theoretical yield. So we'd have 1.00 grams minus 0.857 grams multiplied by 100%, or sorry, divided by 1.00 grams multiplied by 100%, which should give us 14.3%. So essentially, these two numbers are actual yield, or sorry, percent yield and our percent error equal 100%. Okay, if you guys have any questions or if you need anything, let me know. And I will see you guys next week. Have a great day. Bye.